All right, so we're going to be covering classifying chemical reactions. The main idea for this lesson is that we could classify different types of chemical reactions based on what's happening with the atoms. We're going to learn 5 different types of chemical reactions. So we want to know what the 5 general types are. We want to be able to predict if a metal will replace another in a compound. We want to understand what the terms oxidation and reduction mean. And then we also want to identify redox reactions. Some new vocabulary for us. We have combustion reaction, synthesis reaction, decomposition reaction, single displacement reaction, double displacement reaction, precipitate, oxidation, and reduction. So these are the 5 different types, and whenever you're reviewing, this is a good graphic to go back to. And so you can see the 5 points of the star. We have the 5 different types: combustion, synthesis, decomposition, single displacement, and double displacement. And then what I really like about this graphic is the pictographs that you see for each. These are very helpful in terms of understanding what's going on with each reaction. So this is always good to go back to. And so the first type of reaction that we're going to go over is a synthesis reaction. And so it says it has a spot for the generic equation. You're going to put A plus B yields AB. And then the generic word equation, you're going to write reaction in which 2 or more substances react to produce a single product. So you could simplify that to 2 or more substances combining to form a single product. So for synthesis reactions, what we have is we always have smaller compounds combining into larger compounds. And so when the smaller compounds combine into a larger compound, they're making something that's bigger. So in this example, I got you, Ava. In this example, we have sodium and chlorine coming together to form sodium chloride. We've seen this reaction in a video previously. He takes the sodium metal, he heats it in the burner, and then he dips it into the chlorine gas, and it forms sodium chloride. So we could see sodium by itself before the reaction, as on the reactant side. We have chlorine by itself before the reaction takes place on the reactant side, and then on the product side we have sodium and chlorine bonded together. Since we have 2 things, they're forming new bonds and they're combining into something bigger. We call this a synthesis reaction. What are we synthesizing? We're synthesizing sodium chloride. Here's another example of a synthesis reaction. We did this a little bit more slowly. We did the same reaction but in a crucible. And so we took our magnesium, we had the closed crucible, and we heat it. And then as it heats, it oxidizes. Okay? This is a form of a synthesis reaction because we're taking magnesium, which is by itself, we're taking oxygen, which is by itself, and we're combining them into a bigger compound, magnesium oxide. And so you can see the actual pictures of this happening. Here we have a little coil of magnesium ribbon. They light it on fire, the oxygen comes in, the oxygen comes in, and we form our magnesium oxide compound. So 2 things coming together to form a compound. And so we could look at the particulate diagrams down here as well. We have magnesium, and then oxygen is these little molecules in the air, and then in the end they're combined. So 2 things coming together to form a compound. If you look closely, there is this little symbol above the arrow right here. That is a capital Greek letter delta. Whenever you see a delta over an arrow, that means heat added. And so that's the energy required to get that reaction going. Here are some more examples of synthesis reactions. All these ones involve oxygen and sulfur being added to another substance. So this top one is the one that we just went over on the previous slide. You can combine rubidium and sulfur for rubidium sulfide. If you go down further, you could see some common ones like this one. We have iron and oxygen creating iron. This is iron 2 oxide, and then down here it's iron 3 oxide, which is the reaction for rust. So this last one, this is the combustion reaction that we did in our mole ratios lab. Hydrogen plus oxygen yielded water. All of those are synthesis reactions because we have 2 things coming together to form something larger. So another example that's very common is the generation of photochemical smog. And so whenever you have very high temperatures, the nitrogen in the air that we breathe, remember the air that we breathe is 78% nitrogen, 20% oxygen, so there's a lot of nitrogen. So with very high temperatures, nitrogen can break apart, and when it does that, it can combine with oxygen molecules that are also present in the air, and it can form this nitrogen oxide or nitrogen monoxide. So this gas right here. And then this gas reacts with more oxygen and produces this nitrogen dioxide, which is what we know as photochemical smog. And so in the presence of the UV rays, the nitrogen monoxide forms that photochemical smog, and that's what decreases the visibility in cities. And so that is a synthesis reaction. Okay, it's a reddish-brown gas that irritates the eyes and is damaging to the lungs. We have some more students coming in. Did I see? Okay, yeah. Okay. So this is what the city looks like when it has a lot of smog. And so that's a synthesis reaction that happens naturally in an atmosphere due to the high temperatures produced in a combustion engine, and then forming the nitrogen monoxide, which then reacts and forms the nitrogen dioxide. Here are some other synthesis reactions. These are all forming salts of halogens. So sodium and chlorine gas forms our sodium chloride. We saw that one. Potassium and iodine forms potassium iodide. So all these, we have two things coming together to form a compound. So smaller substances forming something bigger. With oxides, so calcium oxide in water creates calcium hydroxide. These are all, just always look what's going on overall. If I'm starting with more substances and ending with less substances, that's usually a strong indicator that I have a synthesis reaction. The next type of reaction is the exact opposite of a synthesis reaction. It is a decombustion reaction, or decomposition reaction, sorry, a decomposition reaction. And so the generic equation for this is AB yields A plus B. So we have AB, the compound AB, breaking apart into A and B. And so if you look at your notes for the synthesis reaction, you'll notice that this is exactly the opposite reaction. So these are complementary reactions. So the synthesis builds things together, builds them up, makes new compounds, makes larger molecules, whereas the decomposition takes those compounds and the larger molecules and it breaks them down into smaller pieces. And so for the general word equation in your notes, you could put a single compound breaks down into two or more elements or new compounds. And so the thing that you should also note in your notes here is this piece down here. It says decomposition reactions often require an energy source. So you could just say need heat, light, or electricity, usually. So you usually need heat, light, or electricity. So if I were to have, let's say, hydrogen peroxide, H2O2, hydrogen peroxide breaks down into water and oxygen. And so they ship it in a brown bottle, and when you buy it at the store, it comes in a brown bottle. And the reason why is because they don't want light coming in there to break down the hydrogen peroxide into water and oxygen. Because over time, if you have a hydrogen peroxide bottle that's old enough, all of the hydrogen peroxide is broken down into oxygen gas and water. So if you have a bottle that's been sitting in your cabinet for years and years and years, in all likelihood, it's no longer 3% hydrogen peroxide. It's probably 1% or less hydrogen peroxide, and with the rest being water. Okay, so there are some types of chemicals that break down over time due to the presence of the heat or the light. Here's an example of a decomposition reaction. Back when mercury used to be shipped to schools for use in chemistry labs, they would ship it in the form of mercury 2 oxide. And so instead of shipping the metal, because it's a liquid, they would ship it as the compound hydrogen or mercury 2 oxide. And this compound, all you have to do is heat it, and when you heat it, it decomposes into mercury and oxygen gas, the oxygen gets let into the room, and you have the mercury metal being left behind. And so here we see the compound mercury 2 oxide. It's being heated. We see the little capital delta sign over the reaction arrow symbolizing that it's being heated. And then we get two simpler substances as products, the mercury and then the oxygen gas. And so we're taking a compound and breaking it down. And so if you look closely at this picture here, we can see the orange compound, the powder mercury 2 oxide, and then as it's heated, the oxygen is being driven off. So you can see that little cloud here, that's the oxygen, and then the mercury metal, the liquid, is condensing on the side of the test tube there. So here are some decomposition of binary compounds. So this one down here is the one that we just looked at. If you were to take water and apply electricity, you could separate it into hydrogen gas and oxygen gas. Carbonates like calcium carbonate, which is chalk, if you heat them, you can get calcium oxide, which is lime, and carbon dioxide. Calcium hydroxide, calcium hydroxide. Is that the one that was? No. This is calcium carbonate being heated. This one is calcium hydroxide being heated, and you can get lime and water. Here is potassium perchlorate. You heat that, you get potassium chloride salt and oxygen gas. Sulfuric acid, you can heat it and get sulfur trioxide gas and water. So there's all these different decomposition reactions where we're starting it with something larger and we're doing something, usually adding an energy source. It could be light, heat, electricity. In some cases, there are biological organisms that can break down compounds. For example, in our mole ratios lab the other day, we took hydrogen peroxide and we added a yeast suspension. Well, what yeast is that it's a fungus that breaks down hydrogen peroxide into oxygen gas and water it. So hydrogen peroxide is actually toxic to the body, and so there's also enzymes in your body that can break down hydrogen peroxide. So if you put hydrogen peroxide on a wound, it'll actually form a couple bubbles, because it's going to be breaking down. The enzymes in your body are breaking down that hydrogen peroxide. When you took biology class, you did a lab where you had little pieces of liver. You had frozen liver, cooked liver, and normal room temperature liver. And then you also used potatoes, cooked, raw, and frozen potatoes, and you added hydrogen peroxide. And depending on whether hydrogen peroxide bubbled or not, you were seeing the activity of that enzyme. Well, what that enzyme was doing is it was a decomposition reaction. It was taking the hydrogen peroxide and it was breaking it down into water and oxygen. So that was an example of a natural decomposition reaction. Another natural decomposition reaction is cellular respiration. We take glucose, C6H12O6, and we break it down into oxygen. No, we break it down into, not oxygen. We break it down into water and carbon dioxide. So taking the glucose, breaking it down into water and carbon dioxide, we're getting smaller molecules, and that's a decomposition reaction. We've learned that photosynthesis is the opposite of cellular respiration. So if cellular respiration is a decomposition reaction of glucose, well, the production of glucose in photosynthesis must be a synthesis reaction. That's why we have the term photosynthesis. Photo means we're using light and we're undergoing a synthesis reaction. We're taking carbon dioxide and water and forming those large sugar molecules, the glucose molecules. Okay, and so we have those synthesis and decomposition reactions are complementary reactions. One builds things up, the other one breaks things down. So going back to that image at the beginning of the slideshow, let's look at the pictographs that it provided. So for the synthesis reaction, that's actually this equation, this example equation that it's providing is the equation for photosynthesis. We're taking smaller molecules, 6 carbon dioxide, 6 water, and we're forming one big glucose molecule. So we're taking smaller things and building them up into something greater. Oxygen being a byproduct in this case. Decomposition, they have the cellular respiration. We're taking that glucose, we're breaking it down into the 6 CO2 and the 6 H2O. Look at the pictographs we have here. For the synthesis reaction, we're taking the puzzle pieces and we're putting them together. Okay, that's a good reminder that a synthesis reaction, we're taking smaller pieces and we're building something larger. Individual elements forming a compound or a molecule. In this case, for photosynthesis, we have we have 2 different smaller molecules forming a much larger molecule. For the decomposition, we have something that's already put together and we're breaking it apart into its constituents. So we have the puzzle of 4 pieces being broken down into its 4 separate pieces. So just like we have glucose being broken down into smaller molecules of CO2 and H2O. I think it's very apparent that glucose is a large molecule. Look how many atoms we have involved. 6 plus another 12 is 18, plus another 6 is 24 atoms large for this glucose molecule, whereas CO2, that's only going to be 3 atoms, and we have 6 of those molecules being made. And then water is also 3 atoms, and we have 6 of those molecules being made. And so we're getting a bunch of smaller pieces in this decomposition reaction. And just like we're using a bunch of small pieces to put them together into a big glucose molecule in the synthesis reaction. All right, moving on to double replacement reactions. Depending on the book or the video that you're watching to learn the chemistry, you'll see the terms double replacement and double displacement used interchangeably. Okay, replacement, displacement, it doesn't really matter which one you're using. The focus here is that it's double. We're doing 2 things simultaneously. And so the general word equation for this is 2 ions exchanging between compounds. So exchange of ions between compounds. And then if you look at the general word equation, or the general equation rather, let me zoom in. We have this one, AX plus BY yields AY plus BX. And the color coding can also be helpful. Okay, so it might be beneficial to color code this in your notes as well. And so what we see going on is everything gets new partners. So if we focus just on the reactant side, AX plus BY, A is with X, B is with Y. But on the product side, A is no longer with X, it's with Y, and B is no longer with Y, it's with X. And so everything gets a new partner from left to right. So A was with X, now it's with Y. B was with Y, now it's with X. So we're just swapping. Okay? Let's look at an actual example for this. So we have the reaction between calcium hydroxide. It's aqueous, which means it's a salt dissolved in water. And we have hydrochloric acid. Again, aqueous, it's a gas dissolved in water. Aqueous means dissolved in water. And then we're forming a product, calcium chloride, which is also aqueous, so calcium chloride dissolved in water. And then we're forming a liquid. We're forming water itself. And so when we look at this reaction, calcium starts off being with hydroxide. Go to the product side. Calcium is no longer with hydroxide, it's now with chlorine. So we swapped them. Hydrogen on the reactant side started with chlorine, but in the end, chlorine ended up with calcium, and hydrogen ended up with the hydroxide to form water. And so we're swapping places for the ions. So whenever we have a double displacement or double replacement reaction, we're usually going to form, almost always these types of reactions happen in aqueous solution. We're taking one aqueous solution and then another aqueous solution, so 2 substances dissolved in water, and we're combining them. In our mole ratios lab, we did this with 2 separate reactions. We did it with a lead-2 nitrate solution, and we did it with a potassium iodide solution. We combined them, and we formed that nice, pretty yellow, gold-looking precipitate that came out of solution. And then in the second part of the lab, part 1B, we took lead-2 nitrate again, and this time we combined it with sodium oxalate, and that one formed a white precipitate. Either way, we took 2 aqueous solutions, combined them, and formed a solid. Whenever we have a double displacement, double replacement reaction, we're combining 2 aqueous solutions and we're forming a solid, which we call a precipitation reaction, a liquid, in which we can call that a neutralization reaction, or a gas. Okay? Solid, liquid, or gas is being produced. So we're starting with both reactants being aqueous, and then the product, one of the reactants is a solid, liquid, or a gas. And then that liquid is typically water, especially if it's an acid-base reaction. Acid-base reactions are double replacement reactions that form water and a salt. So we need to know the term precipitate. Precipitate means a solid that forms when 2 solutions are combined. Since the solid has a greater density than the liquid, it will sink to the bottom, given enough time. It's important to note that due to the law of conservation of mass, whatever goes into a reaction must also come out. So while we are forming that solid, we're not actually gaining any mass, it's just rearranging. So if I were to weigh the reaction before and weigh it afterward, it's going to be the exact same. So here's an example, another example of a double displacement reaction. So first off, what kind of reaction am I going to have? Well, I can see it's producing a solid in solution. And so here we have our solution, and then we're putting another solution in, and as it combines, it's forming this cloud of this solid. And so it's forming a solid, therefore this is a precipitation reaction. We're forming a solid white precipitate. And so we have sodium sulfate, which is a salt. It's dissolved in water. That's what aqueous means. And we have barium chloride, another salt, and that's dissolved in water, and that's what aqueous means. So we have sodium sulfate, barium chloride, and we're combining these, and when we combine them, they form this solid barium sulfate and sodium chloride as another product. So what happened? Well, we took sodium and barium and we just switched their spots. Sodium was with sulfate, but when we switch it, barium's with sulfate, and so that's where we get this barium sulfate being formed. On the reactant side, barium was with chlorine, but we switched it. Now sodium is with chlorine, and that's where we get the sodium chloride. So we're switching the ions, and we get new products formed. It's important to note that these subscripts, like 2 and 2, sulfate is always SO4, so we're not talking about that subscript in this case. So sulfate goes through to the other side. But this 2 with sodium does not follow through. See how over here on the product side, sodium does not have that 2 after it? Subscripts will never follow through to the other side of the equation. They can never go to the other side of the arrow, because the purpose of subscripts is to cancel out ions, the charges of ions. If the purpose of a subscript is to cancel out the charge of an ion, and we're recombining the ions, well, we need to refigure out those subscripts. And so we have sodium is a +1 ion, chlorine's a -1 ion, sulfate's a -2, and barium's a +2. Okay, those are the charges of those ions. Those are always the charges of those ions. Well, on the left side, on the reactant side, sodium's with sulfate. So these two are forming a compound. Well, it makes sense that we need 2 sodiums then, because we need 2 to cancel out the -2. So we end up with a 2 after the sodium down here. But on the product side, sodium is no longer with the sulfate, it's with the chloride. So we could see when sodium and chloride combine, we have a +1 and a -1. It doesn't make sense to have 2 sodiums this time because we're combining with a -1 ion instead. We started it off with a -2 ion, that's why we needed 2 of them. That's why we have the subscript of a 2 right here. But when we combine it with the chloride, we're canceling out a -1, so it makes sense that we only have 1. So when you are making these products, you have to reassess the situation. You have to redetermine what the subscripts are going to be. Megan, go ahead.
How did they get to the sodium chloride
So if you were to tally up all of the elements here, so we have 2 sodiums, and we have 2 sodiums showing up, and then we have 2 chlorides, and we have 1 times 2, so 2 chlorides there. And so how do we get 2 sodium chloride forming? Well, the reason why we get that is if you look carefully, we have 2 sodium here, and we have 2 chloride here. That's enough to make 2 of these. Does that make sense?
Yes.
Okay, that's a good question. All right, so we have to redetermine what these subscripts are going to be because they are combining with different ions. And so it doesn't make sense to just follow the 2 through because that subscript of 2 is not part of sodium's identity. However, its charge is, and its charge needs canceled out. All right, let's move on to the next slide. I don't know how to get my arrow back. Well, we're trapped. I can't do it, guys. Next. I'm still writing that. Okay, whatever. We'll just do it that way. So here's another example of a precipitate forming. Okay, I know it's a precipitate forming because I have this lead to iodide forming. Oh, this is the reaction that we did. This is where we got that yellow precipitate. We did the lead to nitrate and the potassium iodide. So the potassium and the lead switched spots. The potassium started out with the iodide, but in the end, the potassium ended up with the nitrate. The lead started out with the nitrate, but in the end, the lead ended up with the iodide. So that's where we're getting the PbI2. Notice the subscripts are not following through. On the top, on the reactant side, the nitrate has a 2. On the product side, the nitrate does not have that 2. It has a 1. Because in the top, nitrate's combining with a positive 2 lead, but in the bottom, on the product side, it's the nitrate's combining with a positive 1 potassium. So we have to reassess for the subscripts. Control A is the arrow. Gotcha. All right. Here's another example of a double replacement, double displacement reaction. This time, we are forming. Now I don't know how to get the pen back. Man, I need to practice up on my PowerPoint tools. So here, instead of forming a solid, we're forming a gas. So when I combine the iron to sulfide and the hydrochloric acid, we actually get bubbles, and those bubbles would be hydrogen sulfide gas, which is actually a nasty smelling gas, foul smelling. That's the smell of rotten eggs. They actually added to propane gas so you could detect the smell of it. So iron and hydrogen are switching spots. So iron started off with the sulfide, but then we switch and hydrogen ends up with the sulfide, and the product hydrogen sulfide. Hydrogen was with the chloride, but they switch spots, and then iron ends up with the chloride. So we have new products being formed. And so if we follow the subscripts, here sulfide is a -2 charge, so iron is a +2. +2, -2, no subscripts needed. Chloride is -1, hydrogen is +1, no subscripts needed. But here, now sulfide, which is -2, is with a +1 hydrogen, so we need twice the amount of hydrogen in this case, so we have that 2 there. And iron still being +2 and chloride still being -1, we need twice the amount of chloride, and that's why we have that 2 for the subscript of 2 for the chloride. So we had a subscript of 1 here. It does not follow through to the other side. We have to reassess for the subscripts. That's why we have a 2. We had a 1 on the chlorine. It does not follow through to the other side. We have to reassess. We have to cancel the charges. Control A for arrow. Gotcha. All right, here's an acid-base reaction. This time, instead of forming a solid or gas, we're forming a liquid. In this case, it's water. So we have an acid, hydrochloric acid, and we have a strong base called sodium hydroxide. This is lye or drain cleaner. You combine these, and Control P for pen. Hydrogen and sodium are switching spots. Hydrogen was with the chlorine, and now it ends up with the hydroxide, and so we end up with this HOH, which I think you might recognize as H2O, which is water. And so hydrogen was with the chlorine, and now it's with this hydroxide here. So that's right here. Sodium was with the hydroxide, now it's with the chloride, NaCl. So 2 aqueous substances combining to form an aqueous substance and water. I mean, these are tips for guidelines for writing double replacement reactions. It's just what I've been showing you. You switch the cations, and then you figure out what the products would be. Okay, The next type of reaction is a single replacement or a single displacement reaction. These are going to come in two different forms. Regardless, you have a lone element coming in to replace another element that's already part of a compound. So you have a lone element coming to replace another element that's already part of a compound. And so metals, since the metals have a tendency to form cations when they're ionized, metals will replace the cation in a compound. And so in this first case, the metal is replacing the compound's cation. We have A coming in to replace B. Okay, A is replacing B, and then B is off by itself. A is coming in, replacing B, and then B goes off by itself. So X was with B, but now A comes in and replaces B, and now X is with A. So what did the replacing? A replaced B, so A did the replacing. If A was a metal, it's going to replace B. However, if A was a non-metal, then instead of replacing B, it's going to replace the non-metal. So in a compound, we have a metal bonded to a non-metal typically. And so if we have a non-metal coming in, it's going to want to replace what's most similar to it. So the non-metal will replace the non-metal. And so in this form, A replaces X and B is off, A replaces X and X is off by itself. So B was with X, but A comes in and replaces X, and then B is with A. So in reality, we have two of the same thing happening, but it just depends on what's coming in to replace. If we have a metal coming in to replace, it's going to replace the front end of the compound. If we have a non-metal coming in to replace, it's going to replace the back end of the compound. So A replaces B if it's a metal, A replaces X if it's a non-metal. Regardless, we end up with a compound and another lone element. So here's an example of that. This is another reaction that we did in our mole ratios lab to create gas A, which was hydrogen. We reacted zinc metal with some hydrochloric acid. So we see the metal goes in the acid starts to dissolve, and we're forming all of these bubbles. Okay? All of these bubbles are bubbles of hydrogen. And so what happened? Well, we had the zinc comes in and it replaces the hydrogen. So let's look at the formulas here. Zinc is by itself. Zinc is a metal. It's going to replace the front end of this formula. So zinc is replacing the hydrogen. Hydrogen is off by itself. So when zinc comes in and replaces the hydrogen, zinc is then with the chloride. So that's where we form the zinc chloride. And then hydrogen goes off by itself. That's where we form the hydrogen gas. Hydrogen being one of your 7 substances, or one of your 7 elements that form diatomic molecules. So we have to put H subscript of 2. Otherwise it'd be wrong. And notice we also reassess for the subscripts. Chloride started with a -1, but now it has a -2 on this side. It was just a 1 when it was canceling out with the +1 hydrogen, but when it has to cancel out the +2 zinc, we need twice the amount. So that's why we have a subscript of 2. So the metal replaced the hydrogen, hydrogen's off by itself, and then we form the zinc chloride. So what you didn't see in that reaction in your lab is you didn't see the zinc chloride salt being formed, because it was being dissolved immediately. So here's another example. If I take aluminum and lead 2 nitrate, aluminum will replace the lead, and I get aluminum nitrate and then lead metal. Here are some examples. So sodium, we know, reacts with water. The reason why it reacts is the sodium comes in. Whenever you have water in a double replacement or a single replacement reaction, it's often helpful to rewrite it as H as the cation, and then OH hydroxide as the polyatomic anion. That way you could truly see what's going on. So when sodium reacts in water, what's happening is the sodium's coming in and replacing the hydrogen. The hydrogen goes off by itself. So that's where we form the sodium hydroxide, because the sodium is now with the hydroxide, and that's where we form the hydrogen, because the hydrogen went off by itself. And so why does sodium explode in water? Well, it replaces the hydrogen. Hydrogen's off by itself, and hydrogen's a flammable gas, and that's what explodes. We have all that hydrogen being produced, and then there's the oxygen in the air. Hydrogen and oxygen combust. And so what's actually exploding when you put sodium or potassium metal in water is not the metal, it's the hydrogen gas that's being produced when you put the metal in the water. The sodium, the potassium, those alkali metals, they move that hydrogen out of there in a single displacement reaction, and then the hydrogen is what explodes. And here's another example, iron with water. It will actually, has to be in the steam form. This requires a certain temperature. You can't just put a chunk of iron in some liquid water and have this happen. But iron with steam, you can form this iron 4 oxide compound, magnetite, and hydrogen gas. That's a very rare reaction. I should probably eliminate it from the slideshow. Okay, here's another one. If I were to take magnesium metal and put it in the hydrochloric acid, it would react very similarly as did the zinc. Magnesium actually reacts faster. That's why I didn't use magnesium for the lab, because then your gas generator doesn't last very long. So magnesium comes in, replaces the hydrogen. We get magnesium chloride and hydrogen gas. Here are some examples of halogens doing the replacing. If I had chlorine gas and potassium bromide, the chlorine will come in and replace the bromine, because chlorine is a nonmetal. It wants to replace the other nonmetal. Bromine ends up by itself. If I were to take fluorine gas and react it with sodium chloride, the fluorine comes in, replaces the chlorine. Chlorine's by itself, and we get sodium fluoride. And so the caveat about single replacement reactions is they don't always happen. So, for example, let's say that I had, instead of fluorine reacting with sodium chloride, let's say that I had sodium fluoride and chlorine gas. So let's say I wanted to take these substances here and try to react them to produce something else. Well, you might think that the chlorine would just come in and replace the fluorine, but it just so happens that chlorine will not do that. It won't replace the fluorine, it won't replace the sodium. And what it will do is absolutely nothing. Because chlorine is not as active, it's not as reactive as the fluorine is. And so if you compare the activity of chlorine and fluorine, fluorine's more active. So let's hypothetically say chlorine did come in and replace the fluorine. Well, the fluorine is now by itself, and it would immediately replace the chlorine because it's more active. And so if you kind of think about that happening instantaneously, the chlorine comes in and replaces the fluorine, and the fluorine is like, oh no, and then re-replaces it. This just goes to show that this reaction is never going to produce sodium chloride if I combine sodium chloride and chlorine gas, because fluorine is the more reactive substance. So since chlorine is not active enough, this reaction will not take place, and so I can just put NR, no reaction. So here is what we call an activity series, and it has a list of all of the substances based on their reactivity, with the most reactive on the top and the least reactive on the bottom. So if we talk about our halogens, which we were just discussing, fluorine is more active than chlorine. So chlorine can't replace fluorine. Neither can bromine or iodine. Fluorine can replace any of these, chlorine, bromine, or iodine. If I wanted to, let's say, replace chlorine with iodine, I couldn't do it because iodine's not reactive enough. If I wanted to replace iodine with chlorine, I could do that because chlorine's more active than iodine. And we have the same thing going on with the metals. This is called an activity series. We can use activity series to predict whether reactions will actually take place. So we went over synthesis, we went over decomposition, double, single, and then our fifth type is combustion. It's important to note that combustion reactions are just a special type of synthesis reaction. So in a combustion reaction, oxygen combines with a substance and releases energy in the form of heat and light. So in combustion reactions, oxygen combines with everything and releases heat and light. That's all combustion is. We could have a very similar looking reaction, and if it doesn't produce heat and light, then it's not considered combustion. It's just considered a normal synthesis. So our generic equation is A plus O2 yields AO. And so here on the left, I have a propane burner. Someone's camping next to a lake. This looks like a Glacier National Park in Montana, but I don't know that for sure. So here is propane C4H10. We're combining it with oxygen, and then we're adding an ignition source. So this capital delta ought to be on top of this arrow. See if I can alter that. Nope. It's permanently in there. Well, the delta sign should be on top of the arrow to show that we have an ignition source. So the propane combines with the oxygen. It burns, it combusts to form carbon dioxide and water plus heat energy. All combustion reactions of hydrocarbons, so compounds that are carbon and hydrogen, will always produce the same two products, carbon dioxide and water. So whether you're burning methane, propane, butane, gasoline, those are all things, ethanol, those are all things that are going to be creating predictable products of carbon dioxide and water. So whenever we burn our lab burners, our Bunsen burners, we have usually propane, and so propane is going to burn and it's going to create carbon dioxide and water if it's a non-luminous flame, an efficient flame. Sometimes if our flame isn't very good, we could have other byproducts like carbon monoxide and soot, but in a perfect reaction, we're going to get carbon dioxide and water. And so these are all of our types of reactions. This is kind of like a summary table: synthesis, combustion, decomposition, single replacement, and double replacement. You'll notice combustion's up here with synthesis because combustion is just a special type of synthesis. And we have our generic equations for all of them and our probable products. Synthesis, we always form a compound. Combustion, we're always going to form oxides, or in the case of burning hydrocarbons, carbon dioxide and water. For decomposition, we're always forming smaller elements and compounds. Single replacement, we have to use the activity series to assess whether it's going to happen or not. And we're going to have a new compound that's replaced, that's formed when something replaces something in the original compound. And then double replacement always are going to yield a solid, liquid, or a gas. Solid is called a precipitation reaction. So that's a summary slide. And then going back to these pictographs, this is probably your best studying tool, is looking at these pictographs. So synthesis, we have a bunch of things coming together. Decomposition, we have something bigger coming apart. Combustion, we're producing heat and light. That's where we have the little fire pictograph. And then for the single displacement, something's coming in to replace. So in this case, the black one's coming in to replace one of the white ones in the compound, and then the white one's off by itself. So that's an example of a single displacement. And then in a double displacement, everything is new partners. So I can imagine, right here. So if I switch these two right here, the black was with the black, and now it's with the white. The white was with the white, and now it's with the black. And so everything gets new partners in that case. So that's a double displacement reaction. So we need to be able to understand what each of these 5 different reactions are. We need to look at a reaction and determine what type it is. And then the highest level is we need to be able to look at 2 reactants, determine the type of reaction it's probably going to undergo, and then the highest level, the ultimate goal, is being able to look at that and predict the products that it should form. Prior to today, if I gave you 2 substances and I said, hey, I'm going to react these, what are they going to make? You had no clue. You're like, I don't know, something might explode, I don't know. Now, if you look at those reactants and you have the formulas, you can start to make an assessment of what are the 5 different types of reactions I'm going to get, and then I could predict the products, and I could have a pretty good idea of what's going to form. Okay, that's the whole point of learning nomenclature, so I could write those compounds. So now I could start to use those compounds to predict things that actually happen in the real world. You had no business even talking about this in predicting products if you couldn't do nomenclature. Okay, so if you're still struggling with writing compound formulas, you need to really solidify that information and solidify that knowledge, because we need to know that material. Okay, I think that's it for the slideshow. Oh, I have a practice set here. So we have 4 reactions, 1, 2, 3, 4, and we should be able to determine what each of these are in terms of their type. Okay, so this first one, we have an element and an element, and they combine to form a compound. So is it going to be synthesis, decomposition, single replacement, or double replacement? The next one, we have a lone element and a compound, and then we get a different compound and a different lone element. Is that synthesis, decomposition, single, or double? Next one, we have a compound and a compound forming another compound and another compound. Is it single, decomposition, single, or double? Synthesis, decomposition, single, or double? And then the last one, we have a compound forming another compound and another compound, noting that these two compounds that are formed are smaller than the first one. Okay, so take a moment and assign types to all four of these, and then we'll go over them. I'll give you about, I don't know, 40 seconds.
How would you know if it was a combustion reaction? For example, like precipitation or values?
That's a good question. Just from the formula, you can't actually tell. If you have a hydrocarbon, carbon with hydrogen, it's going to be combustion. It's just, you have to be able to recognize certain ones.
Okay.
Usually you'd have to have some type of indication to see. We'll go over some examples. Okay, so let's look at these. This first one, we have an element combining with another element to form a compound. That is synthesis. Next one, we have an element combining with a compound, forming a new compound and a new lone element. That is single replacement. In this case, silver was more active than the hydrogen, and it did the replacing. The next one, we have two compounds combining to form two new compounds. And so this is a double replacement. The silicon and the hydrogen switch spots, and we end up with water and silicon tetrafluoride. And then the last one, we have a large compound, potassium carbonate, breaking down to potassium oxide and carbon dioxide. So a compound breaking down into two smaller compounds, that's decomposition. All right, and so that's it for this lesson, and we'll move on to the worksheet.